This next section is the addition rule and complement. The objectives for this section is to use the addition rule for disjoint events. I'll explain what those are in just a bit. And then use the general addition rule. Okay. And then compute probabilities of an event using the complement rule. So we'll talk about complements towards the end. All right. So first of all, let's talk about disjoint events. Two events are disjoint if they do not have any outcomes in common. Another name for disjoint events is mutually exclusive events. Oftentimes we want to draw what's called a Venn diagram, which is this picture you see here. It provides a useful way to visualize a lot of these probability problems. Okay, so this entire rectangle, the gray portion here, that's our sample space. Everything that's inside there, that's essentially where every data value or every outcome existed. Okay, so that's our sample space. And each circle here, the yellow one is event E, and the blue one is event F. And then there's 3, 4, 5, 6, 7 that's outside of both E and F, but it's still inside the sample space of S. Okay, and we already know how to represent a sample space using set notation. So this particular sample space, everything within the rectangle is 0 through 9. There's 10 elements there, right? 0 through 9, 10 elements. Where events E is 0, 1, 2, right? That's the yellow circle there. And event F is 8, 9, which is that blue circle. Okay, so let's keep that in mind as we answer these questions. So example 1, use the Venn diagram in figure 5.1. Find the probability for the event E. Okay. Well, how did we calculate probabilities before? Well, using the classical method, right? We would say probability event E is equal to the number of ways, or the number of elements in event E, over the number of elements in our sample space. Okay, so this is just a matter of counting the number of elements in each one of these sets. So in our sample space, we said it was 0 through 9, so there's 10 down there. And in E, there are 1, 2, 3. So 3/10 is our probability, right? Or you can write that as a decimal, 0.3, 3/10. 3/10, 3/10. All right. What about the probability of event F? Okay, so same idea. Probability of F equals the number of ways that we can find F over the number of ways S, the number of elements in each set. And again, for F, we just have 1, 2, that's the 8, 9, over sample size of 10. Sample space size is 10, which is 2/10. That can actually be reduced down to 1/5, right? But I do actually like the denominator of 10th because it's actually easy to read. 2/10 is 0.2, right? 2 in the 10th place. Find the probability for the event E or F. Okay, so we kind of have to talk about these OR probabilities. Okay, well, what does it mean for something to be an E or F? Well, it can be an E or F, just like how it sounds, right? So basically, you want to think of this as the unification of these two sets. Anytime you see that word OR, think of union. Okay, so I'm actually going to split this down the middle because I'm going to show you how to calculate this in a couple ways. Let's actually list out that set, E or F. Well, so everything that's in E or F. So we're essentially unifying these two sets up here. So everything that's in E and everything that's in F are going to be placed in E or F. So 0, 1, 2, 8, 9. Right? And if we're looking for the probability of E or F, well, that's the number of elements in E or F over the number of elements in our sample space. Sample space, again, is 0 through 9, so that's 10. And in E or F, we just have to count those. That's 1, 2, 3, 4, 5. So that's pretty straightforward. Okay, 5/10 is 1/2. Or, of course, 5/10 in decimal place. All right, so why did I break this up into two parts? Because very often we don't actually have a Venn diagram or a set notation. So if we have just the probabilities of both E and F here, then we can actually calculate the probability of E or F. And it's done in this fashion using this formula. So if we want to find the probability of E or F, then it's just simply a matter of adding on each probability. Now there is a caveat here, and this only works for disjoint events. I don't think I actually explained what that was in detail yet, but let me go ahead and talk about that after I calculate this. Probability of E, we had it up there. That's 3/10. Probability of F is 1/5, but in order to get the same denominator, let's just write the 2/10 there. And as you can see, 3 plus 2 is 5/10, which is 1/2 or 5/10. All right, so what does it mean for events to be disjoint? And is E and F disjoint? Well, yeah, just from the Venn diagram, it just means that both of these events have nothing in common. Okay, they're mutually exclusive. Okay, they're mutually exclusive. E and F, there's no overlap, as you can see here. Okay, so you might be asking, well, how do you find OR probabilities if there is overlap? Well, that's going to lead us into the next rule on the next page. Okay. Now, the one thing about disjoint events that's nice is that when we're dealing with OR events and looking for the probability of that, it could be extended to more than just two disjoint events. Okay, it can be, if you have E, F, G, ... It's just simply a matter of adding all the individual probabilities. Okay. You won't be able to do that when the events are actually not disjoint. All right, so that's the addition rule for disjoint events. Now we're going to talk about the general addition rule. Whether it's disjoint or not disjoint, this rule will work. Okay. All right, so as you can see here, it's another Venn diagram. We have this sample space where we have, again, 0 through 9. If you were to actually go in there and count them all, that's 0 through 9. And you can see that event E and F, there is some overlap here. You can see there's a 4 and there's a 5 in there. That's both in E and F. Okay, so we'll talk about that in just a second. All right, so again, event E would be 0, 1, 2, also 4, 5. You see that? Event F would be, you see how there's an 8, 9, also 4, 5. Okay. So again, notice that 4, 5 are in both E and F. All right, so let's define this set of E and F. Anytime you see that word "and," you want to think it to yourself, that's the intersection. It's what both E and F have in common with each other. So this is considered not disjoint. All right, and in this case, E and F is what they have in common, and that is 4 and 5 is what they have in common. And what would be the probability of E and F? Well, it's the number of elements in E and F over the number of elements in the total sample space. Again, we still have 10 elements, 0 through 9. And in E and F, there's 2, right? There's 1, 1, 2. 2/10 reduces down to 1/5, or 2/10. All right, now we're going to use the figure above, the same example, and we're going to just answer a bunch of other questions. Find the probability of event E occurring, just like before. Probability of E is the number of elements in event E over the number of elements in our sample space. Event E, it's over here, so there's 1, 2, 3, 4, 5. Yep, that's 5. Over a sample space of 10. That again is 1/2, or 5/10. And then we can do the same thing for F. Number of elements in F. Number of elements in our sample space. Where's F at? Over here. You can see it's 1, 2, 3, 4. So we have 4/10. That can reduce down to what? 2/5? Yeah. Again, 4/10 is the decimal equivalent. All right, now they're asking, what's the probability of E or F? Okay, so again, I'm going to split it down the middle before I show you the formula shortcut. E or F. Okay, I want to write down that set. All right, so remember what E or F means. It means if we were to unify these two sets, E and F, what would they have? Not what they have in common, that's the intersection. It's E or F, we're unifying the two. Okay, so we would have to start off with E, which is 0, 1, 2, 4, 5. And then we go over to, so we would have to have all these, and also everything in F. But you see how 4, 5 is repeated, so you just don't repeat those. So I would do 0, 1, 2, 4, 5, and then 8, 9 is the only additional ones. So let's say 0, 1, 2, 4, 5, and then of course F only adds on 8, 9. So essentially we unified these two sets, and the probability of E or F in this case is, well, the number of elements in E or F over the number of elements in our sample space. Alright, so if we just count that, 1, 2, 3, 4, 5, 6, 7, we get 7. Sample space is 10. That doesn't reduce, or 7/10. Okay, so that seems pretty easy enough. Now again, you don't always have access to these lists of sets. Okay, a list of events, E or an F. Sometimes you just have the probabilities. Okay, so let's see what happens if we were to use that rule from before for disjoint events. So probability of E or F. Okay. Well, in the previous section, you see how it was just simply probability of E plus probability of F. Let's see what happens when we do that in this case. Okay, as you can see, there's an adjustment for the general rule. Alright, so probability of E plus probability of F. Okay, so what did we actually do there? Probability of E up here is 5/10 plus probability of F, right, that is 4/10. If we were to add those up, we would not be getting 7/10 like it should be. We would get 9/10. Okay, and that would be wrong. Okay, and why is that wrong? Well, it's because you're accounting for their intersection twice. You're accounting for these 4 and 5 twice. When you count it in E, and also when you count it for F. So what we want to do is remove that replication. Okay. So what would be, how would we remove that? Well, we would have to remove their intersection, which is this thing right here, the 2/10. You see that? So that's why this formula, the general rule, removes their intersection. Okay, because you were double counted it essentially. If you double count it, you want to remove it once. So you subtract off E and F, and that, of course, from above is 2/10. They all have the same denominator of 10. 5 plus 4 minus 2, that gives you 7/10. Okay, so this business here removes any double counting. All right, let's go ahead and do a bunch of examples here. So this first example has to do with a deck of cards. So let's just get familiar with the deck of cards. What we have here is there's 52 cards here, and each one of these rows here are called suits. Okay, this is the clubs, spades, hearts, diamonds. All right, those are called suits. Okay, it doesn't start with 1. There is no 1 card, but it does start with the ace, and it goes 2 through 10, and then the last 3 are jack, queen, king. These are also known in total as face cards. And also you can break it down into black cards and red cards. All right, black and red. Okay. So the nice thing about this is that each particular card has many characteristics, right? So for example, if I were to just pick this one at random, that's a 9 of diamonds, right? Its suit is diamonds. It's 9. It's also a red card. It can also be an odd number. You know, it can have a lot of different characteristics. Multiple of 3. Okay, so let's go ahead and answer the following questions. Now, it does say that at the very top that Becky has a standard deck of 52 cards and wants her friend Rachel to draw a card. After Rachel draws a card, she puts it back into the deck. So every single time she draws a card, that card gets put back into the deck. So every subsequent draw from the deck is from a deck of 52 cards every time. Okay. Later on, we're going to talk about those events being independent from each other, and we'll define that later. So find the probability for Rachel drawing a queen. Okay, so the probability of drawing a queen. So I'm just going to write probability of queen. So you see that we're not going to we don't really have a set notation like we had in the previous examples, but we have this picture here. Okay, so we have to just count all the queens. Well, there's 1 for each suit, so there are 4. Right? So the number of queens over the number in our sample space. So there's going to be 4. Number of our sample space. The entire deck is made up of 52 cards. And that should be able to be reduced, right? 4 goes into 52 13 times, so 1 in 13. Okay, so 1 out of 13 of the cards is a queen. Okay, so that doesn't really... you can have a decimal equivalent, but it won't terminate as a decimal place. So I'm just going to keep it as a whole fraction. Find the probability for Rachel drawing a spade. Okay, so probability of a spade. Well, that's the number of spades over the number of cards, which again is a deck of 52 cards. Number of spades, well, that's that second row right there. And for each suit, there are 13 cards. So there are 13. Okay. As you may imagine, just because of there's 4 rows of equal size, it should be 1 and 4, right? So 13 does actually go into 52 4 times. So 1 and 4. All right, let's keep going. Find the probability for Rachel drawing a spade or a heart. Spade or a heart. Okay. So probability of spade or heart. Okay. For these OR probabilities, just like before, we had 2 situations, whether these 2 events are disjoint or not disjoint. So the way you want to ask yourself is, does there exist a card that is both a spade and a heart? Well, let's look up here. The spades are all these guys. The hearts are all these. Is there any overlap? Is there any intersection here? Well, it looks like there's not, right? There can't be a card that's both a spade and a heart. So we would say that these 2 events are disjoint. These are disjoint. So if they're disjoint, then we can simply use the rule that says probability of spade or heart is simply the probability of the sum of the individual probabilities. Okay, and we know for spade, we know that to be 1 and 4. Let me actually write it as with a denominator of 52. Just because we're going to end up having to get a common denominator anyway. So 1352. Hearts. There's the same number of hearts that there are spades, right? So hearts, again, are 13 over 52. And, of course, 13 plus 13 is 26 out of 52. And that's exactly 1/2. So half the cards are either a spade or a heart. So that makes sense, right? All right, let's continue. Here's another OR probability. These are all OR probabilities. What's the probability of Rachel drawing a queen or a spade? Okay, again, we have to ask ourselves, are these 2 events disjoint, queen and spade? So if these 2 events have nothing in common, or these 2 sets have nothing in common, then they're disjoint. But if there's a card that is both a spade and a queen, then they're not disjoint. Okay, so let's go up here, and well, here's the spades, here's the queen, and of course they're going to intersect right here. See that? So we're going to have all the spades, all the queens, and they have 1 in common. Okay, they have 1 card in common. That's their intersection. Okay, so what we don't want to do is double count that. Okay, so that means we have to use the general addition rule. Okay, so this is not disjoint. So if we're looking for the probability of queen or spade, then we use the probability of queen plus probability of spade. And we can't just stop there because these are not disjoint events. We have to subtract off any overlap, any double counting. Probability of queen and spade. And that word and indicates intersection. Okay, so there's going to be 3 fractions here. Probability of obtaining a queen, well, that was from part A. That's 1 in 13, or let's keep it in with a denominator of 52, so it'll be 4 out of 52. Spade, again, that's part B, 13 out of 52. And queen and spade. Again, this is intersection. Let me just point to that intersection. How many cards are both a queen and a spade? Well, it can only be 1, right? That's the intersection up here. So there's 1 and 52. All right, if you were to add 4 plus 13 is 17 minus 1 gives us 16. And of course we can reduce this down. I'm running out of space here, but if you divide both top and bottom by, I would say 4, you would get 4 over 13. 52 divided by 4 is 13. Okay, so that is the probability of getting a queen or a spade. And then finally, the last one here. What's the probability of Rachel drawing an ace or a queen or a king? Ooh, okay, let's see. Well, these better be disjoint because I haven't taught you how to come up with an OR probability for multiple events if they're not disjoint. In fact, we're not going to learn that in this class. It's a little bit beyond the scope of this class. You can look that up online if you want. Ace or queen or king. Okay. Are these disjoint? Again, we have to ask ourselves, are there any cards that are both an ace or a queen at the same time? Or an ace and a king at the same time? Or a queen and a king at the same time? Well, if you look up here, here's the aces, here's the queens, and here's the kings. There's no intersections at all. They're all completely disjoint. So, yeah, these are disjoint. So again, let me just refer to what rule we're using here. What page was that? Back here. Yeah, it's this problem right here. When you have more than just 2 disjoint events, then it's just the sum of all the individual probabilities of each event or of each outcome. So simply probability of obtaining an ace plus probability of obtaining a queen plus probability of a king, and each one of these has an associated probability. Out of 52, out of 52, out of 52. How many aces are there in the whole deck? Well, there's 4. Same thing with queen, same thing with king. Same denominator, 4 plus 4 plus 4 is 12. And you should be able to divide both the numerator and denominator by 4. 3 13ths. Alright, next example. Consider the data shown below, which represent the marital status of males and females in the United States in 2010. So this is bivariate data. Basically, there's 2 variables here. It has your sex, male, female, versus marital status. Okay. Anytime you have a table like this, you want to automatically create totals columns and a totals row. Okay, so that's what we have here. And let me go ahead and fill that out. So if you just add 40.2 plus 34.0, you're going to get 74.2. And so on. Let me go ahead and fill that out. And then same thing for these columns here. Now, this here would be considered the grand total. All right, that's basically every one of these values being added up. You can either calculate that by adding this row, this totals row, or the total column. You should get the exact same number. If you don't, then you did something wrong. Okay, if you add those up, you get 242.2. Okay, so 242.2 million. Okay, so that seems to be like the entire adult population of the United States in 2010. That makes sense. Let's answer some questions now. Determine the probability that a randomly selected U.S. resident is widowed. So you notice how they did not specify the sex, male or female, right? So they're literally just asking for probability of widowed. So we're randomly selecting one of these people. So the denominator should be the grand total. Okay. And how many are widowed? Well, 14.4. And in this case, I do want to round to some decimal places. I'm going to go ahead and choose 3 decimal places. It's not specified in the notes, but I'm going to go ahead and do that. So I'm going to round it to 3 decimal places. 0.059. All right, so that's about 6%. So we're saying 6% of the adult population is widowed. Determine the probability that a randomly selected U.S. resident is widowed or divorced. Again, this is an or probability. Anytime we're dealing with or probabilities, you have to ask yourself, is there anyone that can be widowed or divorced? Well, technically you can, but not at the same time. Or at least when they were surveying these people, you could only make one choice. Yeah, you cannot both be widowed and divorced, right? You see how there's no intersection, right? They don't intersect with each other. So yeah, disjoint. So widowed or divorced. Okay, so if they're disjoint, it's simply just the sum of their individual probabilities. Okay, and if we have room here, there's going to be 2 fractions being added. The denominator is going to be the same in each case, 242.2, right? That's the grand total. Probability of randomly selected a widowed person, well, that's that 14.4 plus how many are divorced? That is 23.8, if you can see that, which is 38.2 over 242.2. And that gives us, if I'm rounding to 3 decimal places, I get 0.158. So that's close to about 16%, 15.8%. All right, let's keep going. Determine the probability of randomly selecting a U.S. resident that is male or widowed. Okay. Again, we have to ask ourselves with these or probabilities, are these 2 events disjoint? Does there exist people that are both male and widowed? Well, yeah. The intersection of males, these are all the males, and these are all the widowed. So the intersection here is right there. This is not disjoint. So we have to use the general rule. So the probability of male or widowed is equal to the probability randomly choosing a male plus the probability of randomly choosing someone who is widowed. And if we were to do that, then we would be double counting that intersection, so we have to subtract it off once. Probability of male and widowed. Again, all these fractions have the same denominator of 242.2. What's the total number of males? Well, it looks like it's that first column, the total in the first column, 117.8. Number widowed, again, that's that one over here, 14.4. If you were to add those 2 numbers up, you would essentially double count that 3, right, their intersection. So that's why we have to subtract that off. Subtract off the 3.0. You just want to account for it once, not twice. Let's go ahead and add those 2 numbers up and subtract off the 3. What do we get? I get 129.2. Divide that by 242.2. And if I'm rounding to 3 decimal places, I get about 53.3%. 0.533. All right, now we're going to talk about the complement rule. So simply speaking, the complement is essentially the opposite of any event, okay, or not a certain event occurring. All right, so in this Venn diagram, it's what's in green is just event E, okay, and everything that's outside of E, that's within our sample space, would be not E, okay. So what you'll notice here is that the probability of E plus the probability of not E, or the complement of E, has to add up to be 1. Because one of these things must happen. Okay, if event E happened, then the complement event did not happen. And if the complement of that event happened, then we know that that event did not happen. Okay, so there's a few notations here that you'll probably run into. Some textbooks use the complement of a certain event to be represented by a superscript. This is also sometimes shown as like E with a bar on top, something like that. And I've seen other notations too. Okay, so there's not one universal notation for this. Okay, so if you have this equation here, which should make sense, right? Probability of an event plus its complement has to be equal to 1 because one of these things must happen. Then if we were to solve for the probability of the complement, then we would get 1 minus the probability of that event, E. Okay, so that should make sense. Let's illustrate that with a couple examples. Using Becky's deck of cards, what would be the probability for Rachel not to draw a queen? Well, not to draw a queen, well, that's the complement of getting a queen, right? So probability of not a queen, I guess if we're using the notation, we can call this queen complement. That would be 1 minus the probability of obtaining a queen. Okay, so there are what? 4 out of 52 cards that are queens. We can make our lives a little bit easier and reduce this down. We know that 52 is divisible by 4, so we get 1 over 13. And if we get a common denominator, that 1 can be converted to a 13 over 13 minus 1 out of 13. And 13 minus 1 is 12 out of 13. All right, so that should make sense, right? If there's 1 out of 13 cards are a queen, then what's the probability of not getting a queen? Well, 12 out of 13. Next example. The probability that Luis will pass his test is 0.67, so a 67% chance of passing. What's the probability that he will fail his test? The thing we have to recognize there is that passing and fail are complements of each other. So if we're trying to find the probability of fail, well, that's the complement of passing, so this could be 1 minus the probability of passing. And if we know the probability of passing is 0.67, then the probability of failing will be 1 minus 0.67, which is 0.33. All right, let's do one last example here. And this is a two-way table here where we have two variables. And in this case, we're dealing with smoking habits versus whether we're dealing with the male or female. All right, so as we can see here, we have pretty much a completed table. We also have all the totals columns here. So all our observations are like right here, and then we have our totals. And then, of course, that's the grand total here. Okay. All right, so let's answer these questions. It says, find the probability that the randomly chosen person is a man. So probability that we get a man. Well, that's the total number of men. In this case, is 533 out of a grand total of 1,064. And if we put that in our calculator and round to 3 decimal places, because that's what they asked, thousandths place, we'll get 0.501, about 50% chance. Find the probability that this person is a heavy smoker, so HS will represent heavy smoker. Well, let me erase all this stuff. I don't want it to get too cluttered here. Heavy smokers. Well, heavy smokers are here, so the total number of heavy smokers is 89. So the probability of getting a heavy smoker is 89 out of 1,064, which in our case, if we divide this, is 0.084. Okay. Probability that the person is a regular smoker. All right, let's see. Well, regular smoker is right next to that. It's these people, and there's a total of 153. So just like the previous one, out of 1,064. If we round to 3 decimal places, put this in our calculator, we get 0.144. All right, and the more interesting ones are the following two. It's asking, what's the probability that the person is a regular smoker or a heavy smoker? All right, anytime we're dealing with one of these or probabilities, we have to ask ourselves a question. And that question is, are these two events disjoint? Again, disjoint means that they have no common intersection. Okay, so now they don't have any outcomes in common. All right, so let's go ahead and go up to the table here. So I have the regular smokers already highlighted there. So what about heavy smokers? Well, it doesn't look like there's any overlap, right? So you can't, in this case, you can't be a regular smoker and a heavy smoker at the same time. At least in this survey, you only were able to choose one. So the probability of getting a regular smoker or a heavy smoker, well, if these are disjoint, then we just have to use the regular addition rule for probabilities. Okay, and that simply says that for this OR probability, that's going to be the probability that of each event added together individually. Okay, and we don't have to subtract off anything in this case because there is no overlap. So if we subtract something off, it would be 0 essentially. The thing here, you want to make sure that you don't use those calculations from part B and C here. It's much better to just use the original fraction. So regular smokers is 153 out of 1064 plus heavy smokers 89 out of 1064. Okay, and we get 242. And of course, if you round that, we get 0.227. Okay, so you always want to use the original given values instead of rounded numbers in all subsequent calculations. Okay, here's another question. Find the probability that the person's a man or a heavy smoker. All right, again, it's one of those OR probabilities, so you have to ask yourself, are these disjoint? Meaning, is there a particular person that would be a man and a heavy smoker at the same time? All right, so let me go ahead and erase these. Well, we have heavy smokers already highlighted there, so I'll just keep that highlighted. And then man, well, as you can see, there is an intersection here. There's 42 people that are both men and heavy smokers. All right, so we're going to count for all the men, then all the heavy smokers, and then when we add those up, we'd be essentially double counting that 42, so we're going to have to correct that by subtracting it off. Okay, so the probability that the person is a man or a heavy smoker, well, that's probability of getting a man plus probability of getting a heavy smoker, and then we have to correct for the double counting by removing the intersection once. So we count for it twice, we have to remove it once. Man and heavy smoker. All right, so again, for men it was 533 out of 1064. Heavy smokers were 89 out of 1064. And then we have to subtract off that intersection. Let's go back up to the top there. It was at 42. And if you add and subtract the numerators, you'll have the same denominator. We get 580. And as a decimal approximation, we get 0.545. All right, so that's it for this section.